Good afternoon, dear students. We are discussing some methods to improve the output and efficiency of the gas turbines. So today we will discuss about the reheating of gas turbines. In last lecture we discussed about the intercooling of the gas turbines. In that case you find that the work input is decreased, but in this case reheating. What do you mean by reheating of the gas turbines? Actually, in this, the expansion of gases takes place in more than one stage. Like here, combustion chamber 1, combustion chamber 2, compressor, high pressure turbine, low pressure turbine, or this is also called compressor turbine because the compressor is run by this power of this turbine, and this is called generator turbine also because we get output from this turbine. So, what is effect of reheating on the net work done and efficiency? Let us know. This is pressure volume diagram. 1 to 2 isentropic compression, 2 to 3 constant pressure heat addition, 3 to 4 expansion in low pressure high pressure turbine, and 4 to 5 again reheating. 4 to 5 reheating. Next 5 to 6 expansion in low pressure turbine, and we will get here output which can be used for further process in generator, right? So this much amount of work is obtained due to reheating, right? This much 4, 5, 6 actors, right? On TS diagram, as already still is made 1 to 2 isentropic 1 to 2 dash, actual 2 dash to 3 heat addition in combustion chamber 1, and 3 to 4 isentropic expansion in high pressure turbine, 3 to 4 dash actual expansion in high pressure turbine, and again 4 dash to 5 reheating in combustion chamber 2, right? And 5 to 6 isentropic expansion in low pressure turbine, and 5 to 6 dash actual expansion in low pressure turbine. Now, and we know this turbine is used for running the compressor only. So whatever output is there in high pressure turbine, that is used for the compressor. Now main output, any net output, is the work output of low pressure turbine. So with intercooling, with reheating, what is work output of low pressure turbine? Net work with reheating, Cp T5 minus T6 or actual T5 minus T6 dash, right? Cp, it may be Cp gas, it may be Cp air. Actual में this should be of gas, but sometimes in numerical a single Cp is given, so that can be used. If both are given, then we will use Cp gas for expansion and reheating, and again for expansion, and for compressor Cp of air, right? So Cp T5 minus T6 again without intercooling. If there is no reheating, then what will happen? This will again expand from 4 dash to L dash, right? 4 dash to L dash. So what is output without reheating? That is Cp T4 dash minus TL dash, Cp T4 dash minus TL dash, right? Now pressure lines diverges as we go on the right of this. So from here we can see that T5 minus T6 dash is greater than T4 minus TL dash due to divergence of pressure lines on right side, right? So T5 minus T6 dash is greater than T4 dash minus TL dash. That is why work done with reheating is greater than work done without reheating, right? So in this case, net work done with reheating is greater than net work done without reheating. It is shown by W dash, just a symbol, right? Now what is thermal efficiency? W net upon heat supplied, right? So what is W at Cp T5 minus T6 dash upon Cp T3 minus T2 dash, heat supplied from this to this portion again, plus heat supplied during this process, right? Cpg T5 minus T4 dash. I am clearing that general Cp. It may be of air, it may be of gas. That will depend on the value given in the numericals. For compression, air; for other process, gas, right? So from here, the heat added is also increased in reheating, so overall thermal efficiency is reduced. Means, what is our conclusion? That by reheating, net work output is increased, but thermal efficiency of the cycle is also decreased, right? Is it clear? Okay. Now, this is very important term, that intermediate pressure for maximum work output by turbine with perfect reheating. Not only for university exam but also for all competitive exams. This is very important. So H net work, total work done is equal to work by high pressure turbine plus work by low pressure turbine, right? So Cp T3 minus T4 plus Cp T5 minus T6. Mind one thing here, that this expression is derived only for ideal process, means only for isentropic process, okay? And with perfect reheating. Now what we mean by perfect reheating? That the temperature after reheating, means T5, that should be equal to temperature at point 3, means for perfect intercooling, reheating, T5 is equal to T3, right? So Cp T3 outside bracket 1 minus T4 upon T3 plus T5 1 minus T6 upon T5. Now T3 is equal to T5, or you can say T5 is equal to T3 for perfect reheating. So it can be taken out from the bracket. Cp T3 1 minus T4 upon T3 plus 1 minus T6 upon T5, right? Again Cp T3 2 हो गया, आपका minus T4 upon T3 minus T6 upon T5. Now for process 3 to 4, that is isentropic expansion, so we can write T4 upon T3, mind it, we can also write T3 upon T4, or so T4 upon T3 is equal to Pi intermediate pressure. We have to find out this relation for this, right? So Pi upon P3 power gamma minus 1 upon gamma is equal to Pi power x upon P2 power x. It is assumed that x equal to gamma minus 1 upon gamma for simplification, right? And again T6 upon T5, isentropic expansion in low pressure turbine, that is equal to P1 upon Pi power gamma minus 1 upon gamma, or again P1 power x upon Pi power x. Here actually P1, P6, P1 same, so this is pressure P1, and here P3, that will be equal to what? P2, this is pressure, right? So on putting this value, total work done is equal to Cp_T3 2 minus Pi power x P2 power x minus Pi power x upon Pi power x, right? Now for maximum or minimum, we can differentiate the work done. Now what is variable here? This inlet pressure is constant, atmospheric. Now also after compression, whatever pressure will be, that will be constant, right? We know that we have to compress up to this pressure, so this is constant, means P2 is constant, P1 is constant. So what is variable? Pi means intermediate pressure. So we have to differentiate this expression with respect to intermediate pressure. So Cp_T3 d over dPi 2 minus Pi power x upon P2 power x minus P1 power x upon Pi power x. On differentiating, right, from here 2 minus Pi minus Pi, इसको डिनोमिनेटर से न्यूमरेटर में ले गए minus x into P1x. So on differentiating Cp_T3, right, this is on now in numerator. So Cp_T3 constants 0 minus x, pi x minus 1 p2 power x minus x pi minus x minus 1 into p1 power x, because p1 and p2 are constant with respect to pi. Also cp and t3 are constant, right? 2 is a number, so its dimension is 0, right? For maxima and minima, dW turbine upon dpi is equal to 0, as you know. But here cp into t3 cannot be 0 because these are constant, good. And so on putting this equal to 0 and solving, we can find out x p1 I x minus 1 upon p2 x into pi minus x into p1 x. Again it will come in denominator and it will multiply here. So p1 into p2 power x. Again this power will go out. So p1 power x minus 1 plus x minus 1, x plus 1, sorry. This will go multiplied with this side. So x minus 1 plus power will be added x plus 1 and pi 2 power 2x is equal to p1 into p2 power x and pi is equal to root p1, right? So intermediate pressure is geometric mean of initial and final pressure in reheating, but condition is that these expressions are applicable only for isentropic process and perfect intercooling. Perfect intercooling means T3 is equal to T5. This is very important analysis for numerical point of view. Okay, right? Thank you.